In the last videos, we discussed about how do we find equilibrium points and how do we test the stability of equilibrium points by drawing phase line and by linearization technique, right? The next technique is by direction field or the slope field. In both phase line and linearization technique, we took examples of autonomous system. Now, the direction field, if the differential equation is non-autonomous, then the phase line and direction field are hard to apply. Okay, so we'll apply direction field and slope field or slope field method. So, what is actually the direction field or the slope field? Is we draw short pointed line for each time and the solution y, okay, with slope. That pointed short line is for the slope of y prime, okay, or fy or fty in ty plane. Again, so if you have autonomous system, you can use direction field. If you have non-autonomous system, you can still use the direction field method. Okay, so for both type of equation you can use direction field method. So I'm giving you an example with the autonomous because there is no explicit t on the right hand side. Okay, so I'm trying to find out the stability of the equilibrium point by using the direction field method or the slope field method by drawing the slope field. Okay, so what is the equilibrium point here? What is the equilibrium value here? Is dy over dt equals to 0 implies y equals to 1 is the equilibrium value, right? So what we need to do next is we need to draw a line y versus t here, t. Okay, so what we do next is we want to draw for each, because these are y equals to 1, y equals to 2, y equals to 0, y equals to -1, like that, right? 0, 1, 2, -1, and so on. Okay, now, so what we are trying to do is we are trying to draw the short pointed line at for each combination of t and y. Okay, for each combination of t and y. All right. So for t equals to 1 and y equals to certain number, like that. Okay, let's say for t equals to 0 and y equals to 1. So if you take t equals to 0 and y equals to 1, what do you get? Dy over dt. Dy over dt, that is the slope, right? Slope will be, I'm taking t equals to 0 and y equals to 1. So you will get 1 minus 1, that is 0, right? So slope is 0, that's what you get. Slope 0 at ty at 0, 1. This is that 0, 1, right? We will draw a short pointed line with slope 0. Why? Because at 0, 1, this is t is 0, y is 1. That is 0, 1. If you plug in that t equals to 0 and y equals to 1 here, you will get y prime equals to 0. That is the slope is 0. So slope 0 means a horizontal short pointed line. Okay, guys. Now, this is t equals to 1. So this point is 1, 1. T is 1, y is 1. Did you see that? Now, so if you want to find what is the slope at 1, 1, you will, because there is no t, so you just plug in 1. 1 minus 1 is again 0. So the slope at this point is also 0. If you continue this way, this at all time t, when y is 1, this is what you get. Right? That means for a horizontal line, the slope is the same for the autonomous system. You see that? For any line you can say. All right, next is, let us say at 2, 0, what will be the slope? 0, 2. At 0, 2, if t is 0 and y is 2, that means you'll write t is 0, y is 2 on the right side here. 2 minus 1 is 1, right? So the slope here will be 1. You see that? And another, when t is 1, when t is 0, the slope is, and y is 2, slope is 1. When t is 1 and y is 2, the slope is again 1, so 45-degree slope, right? You see that? At here also you do that 45-degree thing. For here also you do the 45-degree, because the slope is 1 at all t values. You see that? Because the right hand side is not depending on t, you get the same slope for all of those. You see that? So similarly at -1, at 0, what do you think? At 0, how would the slope look like? At y is 0, and then t is also 0, right? So y is 0, t is 0 minus 1 is -1, means decreasing, right? Y is decreasing, the slope is -1, maybe like this, right? And at t equals to 1 and y is 0, the slope is again -1. So continue that way. You see that? So you see that? So if you draw the direction field for 1.5, 0.5 like that, so what do you get? Or 0.5, you will get like this. Like this. And for 1.5, you will get like this. Right? See, this one, this line is actually y equals to 1, right? At y equals to 1, the slope is 0 everywhere. Because when you put y equals to 1, there is no t, right? For any t, when y is 1, dy over dt is 0. So the slope is 0, right? Slope is 0 means all these short pointed lines represent the slope. So these short pointed lines are horizontal. You see that? And for little less than 1, they will be decreasing, because if y is less than 1, it will be decreasing. More or less, if y is a lot less than 1, it will be more sharply decreasing, and so on, right? Like this, like that. Okay, and if it is a lot bigger than 1, then it will be more like this. So you can see that if you draw a line like this, then it will look like this, right? You see that? Like this. And you see, because they are saying like that, right? They are showing that direction, meaning that y equals to 1 is not stable. You say unstable. This is the direction field for this differential equation. Okay, and then you can say that y equals to equilibrium point is stable or unstable from the direction field. So I'm going to give you another example that has that is non-autonomous. Okay, so you see that the at every horizontal line, you see that at every horizontal line the slope is same, right? At y equals to 1.5, the slope is -0.5, slope is positive 0.5. At y equals to 2, the slope is 1. At y and so on. Similarly, at y equals to 0, slope is -1. See, at every horizontal line in the autonomous system, so you can write that one for autonomous system, autonomous equation, autonomous ODE, right? You can say that the slopes or direction, right, at all horizontal lines are same, constant, same or constant in the autonomous system. But that is not the case for the non-autonomous, because you will see that there will be t as well on the right hand side. If there is a t on the right hand side, then for every different time you will get different slope, right? So, but there will be some lines or the curve where the slope is constant in case of the autonomous system. So that is called the IsoClients. Okay, so how do we find out the IsoClients? Is in case of the autonomous, non-autonomous system, we will find out the lines where the slope is constant. Okay, so for non-autonomous system, for non-autonomous ODE, we find curves where slopes are constants by setting f of ty equals to c. That is, we will do right hand side equals to a constant c. Because see, for the autonomous system, non-autonomous ODE look like what? The non-autonomous ODE look like dy over dt equals to function of t and y, right? You will see the t explicitly there. Now, when on the graph the derivative will be constant, is if you say dy over dt equals to c, then you will get f of ty equals to c, and then those will be the curves. We will take different values of c, and those will be the curves where the slope is same. Okay, by setting that equals to c and considering different values of c. Okay, we will do one example. Let us do one example. Draw direction field for ODE, ordinary differential equation. The ODE is, let's say, dy over dt equals, instead of y minus 1, I am doing y minus t. There is explicitly t is seen here, right? There is a t, explicit separate t there. Okay, now what we want to do is we want to draw the direction field here. Okay, so how do I draw the direction field here? So I need to first find out the IsoClients. These are called IsoClients. Okay, these are called IsoClients. ISOCLINES. Okay, so what are the IsoClients? Let me write down the solution. The IsoClients are y minus t, the right hand side, equals to c. Okay, so y minus t equals to c. So taking different values of c, what do you get? You will get y minus t equals to 0, y minus t equals to 1. That means y equals to t plus 1, right? And then y minus t equals to 2. That means y equals to t plus 2. Y minus t equals to 3, y equals to t plus 3, and so on. You can take -1, -2 like that too. Okay, so like y minus t equals to -1, so y equals to t minus 1, and so on. Now what we do is, these are the IsoClients. For different values of c, you will get all these different equations. These are the IsoClients where the slope are constant. What will be the slope? We will see that. Okay, let us draw that. All right, so let me draw the vertical line is y, right, and the horizontal line is t. This is ty plane, or x, ty axis. Instead of x, we have t. That's everything is same, right? Now let us do that. So what we want to do here is, let us first draw IsoClients. Okay, IsoClient lines. So IsoClients are y minus t equals to c. I just took that as c as a constant. I'm taking different values of c. I'm going to draw IsoClients with very light color. So y minus t equals to 0. It is like y equals to t, right? Y equals t falls here in the middle. You see that? And y minus t equals to 1 is y equals to t plus 1. Okay, that will go through 1, right? Similarly 2, similarly -1, -2, and so on. Okay, these are the IsoClients that we got. Okay, at these IsoClients, what we're going to do is, we are going to draw the pointed slope for by using the we want to draw the slope by using the very small short pointed line segment. Okay, now let us see that. What is the slope on these? Let's say this is y equals to t, right? This is y equals to t plus 1. Let's write this way. I think it is easier if you write this way. Just write down c equals to 0, c equals to 1. That will be, I think, easier. That is the better way, I think. So let's do c equals to 0. That is y minus t. C equals to 1. C equals to 2. C equals negative 1. Okay, and then c equals negative 2. Like that. Alright, now at c equals to 0, what is the slope? Slope is 0, right? At c equals to 0, c equals to 0 means y minus t equals to 0. If you said y minus t equals 0, then the slope dy over dt, that is y prime, is 0, right? Y prime 0 means the slope will be, the y prime 0 means slope is 0, right? Slope 0 means at each point of this line, the slope is 0, means it is a horizontal line segment, right? Like this. You see that? Slope 0 means a horizontal segment here. Now, at c equals to 1, what do you see? At c equals to 1, that means y minus t equals to 1. That's what it is, right? That is 1. So slope is 1. Slope 1 means what? Slope 1 means 45 degree, right? This is a 45 degree. At any point you consider, that's what you get. You will get the same slope on these lines. Okay. So for the negative 1, c equals to negative 1, the slope will be negative 1, right? Slope will be negative 1, means how would that look like? That look like this. On these lines, right? At c equals to negative 2, it is still bigger slope, right? I mean the more steep, decreasing. Slope is negative 2. How about the positive 2? Positive 2 is more steep, increasing, right? So it will be like, so at c equals to 2, the slope is 2, right? So slope 2 means about 63 degrees. So 63 degree is little at each point. And so on. Okay, now, so there are some points in the between those two isoclines, right? So how do I find out? For example, let's say this is, let's say 1, 2, 3, 4, 5, like that. Now let's say at 2, 1, how would the pointed line look like? At 2, 1, what we do is t is 2, right? And then y is 1, right? This is 2, 1. So plug in t is 2, y is 1. How much is that? Negative 1. You see that? It's negative 1, right? Oh, so it looks like, I think the 2, 1 lies here, right? So you just basically plot those points, all those points that you want to find out the all these coordinate of this point into here, into the right side of the equation, and find out the slope and draw a pointed, little short pointed line with that slope. Okay, that's what we do. Okay, this is how we can feel the direction field. We can draw the direction field. So how would this look like actually? So it looks like the lines are like this, right? You see that? The lines are going like this and then going like that. You see? And then if you draw more curve, it will look like that too. Like that. Okay? That's what the direction field look like. And you may be wondering, what is the equilibrium point here? There is not a single equilibrium point. There is a whole line. Okay? We'll discuss this kind of problem later, but so what I wanted to say here is, how do we draw a direction field for an autonomous and non-autonomous first order ordinary differential equation? Okay guys, thank you very much. There are many online apps available to draw direction field, okay, of a differential equation, maybe system of differential equation, meaning if there are more than one differential equation that are connected to each other, how do we do the direction field. If there is a single equation, how do we do the direction field like that. Okay, so one of that I like is from this website, homepages.bluffton.edu. If you search this as a direction field plotter, something like that, and then you can find so many others. I mean, you can do any one of those, but I like this because it has for one, if there is only one equation, how to do that. If there are system of equation, how to do that. If there are polar coordinates, if there are polar system, like that. So in that case also it is useful. Okay, so here so on this one, what I'm going to show you here is basically, let me make it a little bigger there. Okay, so what I'm trying to do here is so I am doing the last example we did. Okay, so the very last example we had dy over dt equals to y minus t. I mean, if you want to do y, if there is like given as dy over dx equals to something, you can pick that one. If it is given as dy over dt equals to something, then you can pick dy over dt equals to, but that's the same idea. Okay, so we have dy over dt equals to y minus t, and then what I'm doing here is basically, what I'm doing here is basically I am setting the window of between -5 and 5 for x, and for t, and -5 and 5 for y. Okay, and with you can pick many segments or just little segments. It depends on how many you want to do that. Okay, if you want to pick many segments like that for x and for y, you can see better picture, you can I guess. Okay, now so what you do is on the right hand side of your problem was y minus t. You enter that, and then you pick the windows of whatever you want to. Usually we do -5 and 5, but if you don't see the clear picture, then you may have to take the bigger windows there. Okay, and then if you want to see for certain values of like if you want to draw the graph, or if you want to see the nature of the graph, then you can just click here. Okay, so you can click, like if you click somewhere here, then you can see that how the solution goes. Okay, you see that the previously we had the similar graph when we did do by hand. Okay, so this is what you can see. All right, guys, and also there are like plot numerical solutions by different methods, plot the other function, what other function you want to plot to compare that one. Okay, and also there is a how to use this page, so there is idea how to use that. Okay, they have given the hints on that, and the numerical solution tables and everything. So it is given for t equals to this, what is y, for t equals to this, what is y. So it gives you a lot of details of the solution. So this is one of the free online app I like. Okay, that draws the direction field for you for free. But one of the things you can see is it doesn't have the arrowhead. Okay, so you think that all of these have the arrowhead on the right hand side corner, right end of each of these line segments. Okay, so this is the free software, this free app, but you need to know how to do by hand. Okay, but once you know how to do the direction field by hand, you can use the app. If any question asks you to draw the direction field, and then you can copy this. Okay, it says to save the image, click right click the thumbnail of this, you can click this and then save. It was loading, right? It was loading, or you can just take the picture of that and then include, or you can draw x-axis and y-axis, or t-axis and y-axis, and then draw this kind of scenario in your paper. Okay, in your homework. So you can do that. Okay, guys, so this is how you use computer to draw the direction field. All right, guys, thank you.